Hi, so welcome back. In this lecture, we will continue with power series solutions. We will look at something new, some other conditions with which we can also solve differential equations in the form of power series. That would be called the Frobenius method, but we will come to that. So let's say we have this differential equation, which is a second order linear differential equation, but again with non-constant coefficients pt and qt, which are coefficients, non-constant coefficients or functions of time. We don't have to look at this differential equation right now. This is something that we will get to. This will transform into this. But let's just say that, let's just look at a little bit of the theory that is involved in finding solutions to this differential equation using power series. So in the last lecture, we said that if P and Q had a Taylor series expansion around a certain point t0, they were called analytic. Okay, P and Q were called analytic, and we learned how to solve the differential equation using the power series method. So in such a case where P and Q had a Taylor series expansion around t0, in that case, t0 would be called an ordinary point. Okay, so that's the definition. We will go over a couple of definitions here. t0 would be called an ordinary point of this differential equation if P and Q are analytic at t0. Okay, that's the case that we have already solved in the previous lecture. We are going to look at something new today. Suppose t0 is a point where P and Q are not analytic. Okay, in that case, t0 would be called a singular point. Okay, but there are two kinds of singular points. One is a regular singular point where even though P and Q are not analytic at t0, but still if you multiply P by a t and Q by a t square, these two new functions become analytic at t0. Okay, then if this happens, then t0 would be called a regular singular point, and we would have we can solve a differential equation in this case using a power series solution, and that would be the Frobenius method. So even though this is t0 would be a singular point, but because it's regular, or in other words, P and Q follow these two particular conditions, we can actually work out a solution for the problem. However, if this does not happen, that if P and Q are not analytic, and if they don't follow this particular condition given in part A, then t0 would be called an irregular singular point, and we would not generally have a solution by power series using, if t0 is an irregular singular point. Okay, so we are going to concentrate on this one today. Okay, where we have a differential equation, second order linear differential equation with non-constant coefficients P and Q, but they are regular singular points. In other words, this holds. Okay, in this case, how do we solve this differential equation? So if P and Q, if TP and T square Q are analytic, then you can write them as, you can just name them as a different function. I'm calling TP by B, and I'm calling T square Q by C. Okay, just giving them different names. But now that this one is analytic, that's what it says, because t0 is a, by the way, I'm considering t0 to be 0 here because as we did that last time, it doesn't matter. We're taking t to be t0 for the rest of the conversation. Okay, because it's a matter of just translation of the axis. Okay, so we can work out the problem using t not equals 0, and exactly the same theory holds if you put that back in. Okay, anyway, so when this is analytic, you can write this in this form. Okay, this is the Taylor series expansion form or the power series form. Okay, and if t square Q is also analytic, which I'm calling C, then that too will have a power series expansion in this form. and each coefficient I'm calling CL, where L is the index, okay, which is running from 0 to infinity. Now, for this particular type of a problem, once we write down the power series of these two quantities, okay, what works as a trial solution for this differential equation is this one, okay. So in such a case, we will always take a trial solution for this differential equation to be not just a power series, but a power series multiplied by t to the m, where m is also an unknown coefficient, okay, or unknown quantity, okay, undetermined coefficient. So that's what we have to do. This will be the trial solution where all these AKs are also undetermined and M is also undetermined. So of course you can bring this in, and this would, the powers of T will become K plus M. And this will then be the trial solution with which you can find, from which you can find all the values of A, K, and M, and then you would have the exact solution, or you know, the solution, the particular solution, the homogeneous solution, because it's a homogeneous differential equation. Okay, so the objective, of course, is to therefore find these quantities. Okay, the AKs and M. So once we write Tp as B and T square Q as C, and we put those quantities into the differential equation, this is what we will get, okay? So if you, for example, multiply this entire differential equation by T square, you would have a T square. That's what I've done here. You would get this T square X double prime there. You would get a T square P over there, but Tp is already B. So T square P will be TB, okay? It's just multiplying another T on these two sides, on both sides of this equation. And T square Q is already C, so there is a C, okay? So when you have T0, or in this case 0 as a regular singular point, you can just rewrite this differential equation in this form where B and C are analytic functions. And if you stare at this differential equation carefully, this should remind you of a form that we have already done. It was the Cauchy-Euler form. This was exactly the same form, the Cauchy-Euler form of a second order linear differential equation, where the only difference was that these B and C, these two quantities were constant quantities in constant coefficients in the Cauchy-Euler form. Okay, so you had a T square X double prime TB X prime, where B was a constant, but now we have B as a function of time, and you had a Cx in the Cauchy-Euler form, which now transforms into a Ct, which is a function of time. Okay, so with this substitution, you get a form like the Cauchy-Euler form, and we will now solve this differential equation, okay, using the fact that B and T are analytic, okay, and this will be a trial solution, and we will find out what the exact quantities are. In other words, we will find out what the exact solution is, okay. And now, of course, because it's a trial solution, we have to put various quantities into this differential equation. So we need the x prime, which is just differentiating this term by term. Of course, you all know this, the k plus m term will come down, you will get the index reduced by 1. Same thing will happen here. The k plus m minus 1 will come down once here, it'll get reduced by 1 once again, the index, and that's the x prime and x double prime, okay? So we will put these quantities into this differential equation and solve, and find out how we can solve, we can exactly find out what the quantities are, the undetermined coefficients are, and we will have the solution. So let's just do that, okay? So let me anyway, so we remember what B and C were. All right, so let's put that in here. So first of all, Let's work out these quantities. This is all alone. This is x double prime will be this. You just have to put this in here. What about b and x prime? B had a power series expansion, and x prime also had a power series expansion. Let's just do that. So b t with x prime will be, well, b had a power series expansion like this, where L went from 0 to infinity, BL t to the L, and x prime has this power series expansion, which is from, we're using the index k here, so k from 0 to infinity, k plus m ak t to the k plus m minus 1. Okay, let's just work that out. This will be, you can sort of, this is something that we have done in the previous lecture. Okay, you can think of bringing these quantities in here, in other words, multiplying these quantities with each of these quantities here, okay, and you can have a double sum, the double sum. So let's just write this. So if I bring this in here, you have a k plus m, this one, you get the BL, okay, you have the AK, and you get t k plus m minus 1, okay. Now, right, so that's what it is. Now, if you look at it, I want to call k plus m by a name. I want to call it n. Let me call n to be k plus m, okay. Then, if I write this as n, okay, then this becomes what? This becomes, so let's just write that. Or we can do it here itself, okay. If I write this as n, k plus m is n. So you have a n minus 1 over there, okay. You have a n minus 1 over there. And you have n over here, okay, because k plus m is n. Yeah. And what about this L? Oh, sorry, you had the k plus m plus L over there. So k plus m plus L minus 1. That was what it was. Okay. Sorry, I don't want to call this as m. I want to call k plus L as n. Okay. M is something that I need to find. So I will call k plus L as n. Okay. Then this was k plus m. Okay, let's just keep k plus m as it is. And then what about L? L becomes n minus k. Okay, so this becomes n plus m minus 1. Okay, L becomes n minus k. N minus k. And k plus, I'm keeping the k and I'm keeping the m. So, and this one is k plus m as it is. So now in this new form, what would be the two summation indices? Okay. First of all, where will k go from? It starts from k can go up to n maximum. Okay, because B0 is the smallest index. 0 is the smallest index on B. So it starts from 0 to n. Okay, k started from 0, but in this sum, in this new form, it can go up to maximum n. Okay, but of course, n has no limitations. Okay, because this meant this was L went from 0 to infinity and k went from 0 to infinity. In other words, the indices of t went from 0 to infinity. So the indices will have to go from 0 to infinity, okay, or in this case m minus 1 to infinity. So you have to have n going from 0 to infinity. Okay, so that's the concise form of writing it. What about cx? So ct with x, it gets the same form. You just write this one as, I don't know, maybe some other index, CRTR, and x had the form, this is x, okay. X again goes from 0, k again goes from 0 to infinity, ak t to the k plus m, that's it, okay. Well, if you again do the same trick, you will get a double sum. Let's just bring this in here. So you have this CR with AK, and then you have a T to the K plus M plus R. Here I will take K plus R as N. Okay, again, it's the same thing. I'm just writing everything in terms of the same variable as the index. Okay. So if k plus m plus r, so if k plus r is your n now, so this becomes n plus m, okay. I will retain the k, the r will get changed to n minus k, okay, so this will get changed to n minus k. Well, again, k can go from 0 to n at most, because again 0 is the smallest index on C, and again, as before, n will go from 0 to infinity. So those are the two quantities. Okay, so if you put all of these back into this differential equation, let's see what we get. So t square with this x double prime, you just bring the t square in and you eliminate the minus 2. So what you get is summation. What you get is summation k plus m minus 1 t to the k plus m. Okay, that's what you get with k running from 0 to infinity. That's the first term. Okay, this is the second term. Okay, if you look at it, if you add these two terms, you will have this summation n from 0 to infinity as a common term. Okay, and also k from 0 to n as a common summation. Okay, so what you get is, you're going to get n from 0 to infinity and k from 0 to n. These two are common, and that's why we have used the same indices. Okay, then I can also, in each term, these okay, so let's just do that. Okay, well, let's do one by one. So when you have B, this quantity, and you multiply the t over there, you will eliminate the minus 1. So you will get k plus m b n minus k a k t n plus m. Okay. And then for the last one, you just write this one what it is. Okay, n from 0 to infinity, k from 0 to n. This is the ctx. Okay, you get c n minus k a k t to the n plus m. That's what you get, and you have the 0 on the right hand side. Of course, I'm writing this infinite sum from n from 0 to infinity, infinite sum, or the index which goes from 0 to infinity as n. So I will do the same for this particular term as well, because I'm just renaming the index. Okay, I'm just going to call it n. So I will change all the k's to n. Okay, it doesn't matter. Okay, it's a sum which is independent from the rest of the other part, because I want to have the same index. Okay, so we'll just do a bit of, I can rub this out now. We'll just do a bit of simplification, and that will give us the formula. So what can we do? So this actually gives us, so I can take out the n from 0 to infinity. This entire sum, I can take that out common. Okay, because this is common to all the terms. Okay. The t to the n plus m is also common to all the terms, which I will take out common on the other side. Okay. What will remain? Oh, I missed an an there. Okay, because x double prime had the ak's, remember, which I changed to n. Okay. So what we have, if I take out the t n plus m on this side, what I have common over here is, or what I have left over there is n plus m, then n plus m minus 1 an, plus I will have this one, k from 0 to n, which is now this summation is common to these two, so that I can do a little bit of simplification here as well. So I will have k plus m b n minus k ak, okay, plus c n minus k ak, okay, with the ak's. This is just looking at these two sums, and now the entire thing, okay, will be multiplied by t to the n plus m. I hope that is correct. Okay, so you can see that I've taken the summation, the one common summation, out from all three. I've taken the Tn plus m out from all three. So what remains from this one is just this product and the an. What remains from these two are the summations, which is common to both, that I've taken out common in this one. And what's left is this part. Okay, oh sorry, I don't need the ak here because I've taken the ak out common there. Okay. So in these two sums, ak is common, which I've taken out outside of this curly bracket, and so I don't need this one as well. Okay, all right. So this is what remains, and this is what remains of this sum, and that's how the simplification looks. Okay, we can do one more thing here. You can see that there is an an term, and in this summation there is an an term. When k reaches n, when k is 0, when k reaches n, you have the an term here as well. Okay, so let's just take that out. We want to combine the an terms together and keep the rest of the terms as they are. So we'll just have that one last step where n goes from 0 to infinity. What happens if I take out the nth term from here? I will have n plus m minus 1 from here. I'm not writing the an here because I will have an an from this one, which I will take out common. Okay. What I have here is, if I take the nth term, where that is k is n, this is 0, n minus n is 0, n minus n is 0, and this will be n plus m. So I have n plus m b0 plus c0. okay, that all of them will have an as a term. And since I've taken out only the nth term where k is n, the rest of the sum remains. So I will have k going from 0 to n minus 1. The entire thing remains up to there, okay? Bn minus k plus c n minus k. The whole thing with ak. And the entire thing has t n plus m equals 0. Okay. That's it. That's the final form. Okay. Well, now we just come to find. So remember what we had to do. The objective was to find the m and the various AKs. So the one thing that we can do. So I will box this bracket. I would write this. I would box this equation here because it's an important one. You see, this tells you that on the left hand side you have it's a power series, okay, where there's a summation going from 0 to infinity. This entire thing inside the bracket is a coefficient of t to the n plus m. Okay, so this is a power series on the left hand side and a 0 on the right hand side, which is a 0 power series. So each of these coefficients can be equated to 0, and from there we will get many equations from which we can work out m and the AKs, and that's what we are going to do. But before that, we're just going to So, what we're going to do is, one thing is that when n is 0, okay, then this one, when n is 0, this summation does not happen, okay, because when n is 0, the summation cannot go from 0 to minus 1, okay, k cannot range from 0 to minus 1 because n is 0 would mean this upper index over here is minus 1. So only for the case when n is 0, this summation does not happen. For the case when n is more than 0 or greater than equal to 1, this part of the sum remains. So if I can just rewrite this, just one more final step for clarity, I can just write the n equals 0 term separately from this entire sum. So for that I will have, so when n is 0, I will have m minus 1 plus m b0 plus c0, all of this with a0. I'm just taking out the n equals 0 term from this, and the rest of it remains as it is. Okay, so this will be from 1 to infinity, the entire thing remains. You will have n plus m. With this, what would be the power of t for this? It would be t to the m, because you see this will get absorbed in here, and with n equals 0. Okay, all right. The rest of it is n plus m, n plus m minus 1 plus n plus m b0 plus c0 this is with a n, and then summation k from 0 to n minus 1 k plus m b n minus k plus c n minus k ak, okay, and this whole thing with t n plus m equals 0. Okay, so I've just separated out this one term where n is equal to 0, because for that this sum will not have two parts like this one has. Okay, here now there is no problem. Okay, all of these terms will have these two parts. Okay, now, as I said, on the right hand side you have a 0, so you can equate each of the coefficients to 0. The first coefficient that I can think of is the coefficient of t to the m, because t to the m is the smallest power of t in this power series. If you see t to the m, then you have, as n becomes 1, you have t to the m plus 1. Then as n becomes 2, you have t to the m plus 2. So just equating the coefficient of the smallest power of t to 0, you have, and this is called the indicial equation. Okay, just equating the coefficient of the smallest power of t, you have m minus 1 plus m b0 plus c0 equals 0. You have the a0 there, but that's non-zero. We are considering a0 to be non-zero, so I can eliminate that. So what you have is this. And this is a quadratic equation in M from which you can find M now. Okay? So from the indicial equation, in other words, just equating the coefficient of the smallest power of t to 0, you can find the values of M, and there will be two values of M. In fact, if you stare at this quadratic equation a little harder, you will realize that this is the same quadratic equation we found for the Cauchy-Euler form, okay, where the Cauchy-Euler form was just t square x double prime plus t bx prime plus cx equals 0. You had b and c as constants, so this had, the only difference was that you had the b over here and you had the c over here instead of the b0 and the c0. So this is the exact form of the auxiliary equation that we found in Cauchy-Euler form, and that's what we get. The indicial equation actually gives us, if you think of power series in terms of coordinates, the first coordinate kind of behaves like the Cauchy-Euler form. Okay, so it's the same thing. So the Cauchy-Euler form is a special case of the Frobenius method that we're learning today. Okay. All right. For the rest of the indices, for the rest of the coefficients, from this is the case when n is equal to 0. Just equating the coefficient when n is equal to 0. For n greater than equal to 1, in that case, we can equate this whole thing to 0, and in that case we will have n plus m minus 1 plus n plus m b0 plus c0 a n. If this whole thing is 0, I can actually take this sum to the right, and I can give it a minus sign. So I will have a minus summation k from 0 to n minus 1 k plus m b n minus k plus c n minus k, and both of them will have ak common. Okay, that's the form. That's the equation from which you will get each an. Okay. The only thing here is to note is that if, for example, if m1 is a solution of this quadratic equation, okay, let's say, let's just call it m. If m is a solution of this quadratic equation, so this quadratic equation will have two roots. One of them, let me call m. If it so happens that the second root is the first root plus some integer, okay, n, then this will become 0, because you see, if this is also a root, then if you put m plus n instead of m, you would have m plus n, you would have m plus n minus 1, which is this quantity, plus m plus n b0 plus c0 equals 0. If these two are roots, in other words, the two roots are separated by some integer n, this happens for all integer, right? For all integer n greater than or equal to 1. So if the two roots are separated by some integer n, then not just m will give the 0, m plus n will also give the 0. So m plus n giving a 0 in this equation means that this quantity is 0, in which case we can't find a m in, because the whole quantity on the left becomes 0. Okay, we can't find a n for that particular n. Okay, for whatever n is the difference between the two roots, we can't find that a n because the left hand side becomes 0, because m plus n becomes a root of this. Okay, so that's the only case where we have to look at it differently. We will take that case up later, but for now, if the two roots are not separated by an integer, okay, if the two roots of, let me call this equation 1, of 1 are not separated by some integer n, in that case, we can actually find out a n by this formula. We have just divide by this whole coefficient here, this entire quantity. You will have minus 1 by this entire quantity, which is n plus m minus 1 plus n plus m b0 plus c0. And you have this summation k from 0 to n minus 1, k plus m, b n minus k, plus c n minus k. The whole thing will have a k common. This is true for all n greater than or equal to 1. Okay, so this is the formula that we will have to use to find each of these a-n's. And when you find the two m's from here, for example, if the two roots are m1 and m2, then if you put one of them, you put m1 and you find out the a-n's for that m1, okay, and again you put m2 and you find out the a-n's for the second m, or the m2, and you will have the two power series, which will be the two solutions, homogeneous solutions, and the linear combination will give you the general solution. Okay, so in other words, for each m, okay, you can find the coefficients, okay, and they will give you the power series solutions, the two homogeneous solutions. Okay, we'll take up more non-trivial examples in the next lecture. But in this one, we'll just quickly look at how the Cauchy-Euler form is a special case of this one. Okay, if you look at it, the Cauchy-Euler form, if this is the form that is given to you, you can think of the Cauchy-Euler form as a form in the Frobenius case. Okay, so if this is the differential equation that is there in the Cauchy-Euler form, plus t b x prime plus cx equals 0. Okay, now if you think about it, this can be written as x double prime plus b over t x prime plus c over t square x equals 0. Now this is the form that we started with. If you call this p, if this is the P, and if this is the Q, then of course these two are not analytic at 0. Okay, 0 is a pole of P and Q. You can't put 0 as an argument here. Okay, so P and Q are not analytic. However, if as is clear, if you multiply P by T, then you get B, which is a constant, and that's analytic. That's a power series that is just B with T to the 0 and then 0 T to the 1. This is the power series of a constant. Similarly, if you multiply T square with Q, then you have C, which is again a constant, and that is again C with T to the 0, 0 with T to the 1. That's again the power series expansion of a constant. Okay, so this is exactly what we were doing. The Cauchy-Euler form was really in this is a case where 0 is a regular singular point. Okay, and in that case, if I want to, if my trial solution, if I want to find out the solution of this by what we've learned, because the Cauchy-Euler form follows whatever we have learned, it is in the Frobenius method form. If I take the trial solution as T to the M, the summation n from n from 0 to infinity a n t n, if I take the trial solution like I have taken in this case, then I should be able to find this one, okay, the trial solution, or I should be able to find the solution by using this one, this particular formula which I've just found out. So again, as I said, that this is the this is the auxiliary equation of a Cauchy-Euler form. So you will have the Cauchy-Euler form auxiliary equation, which will be m minus 1 plus mb, because you see b0 here means the 0th coefficient, in other words coefficient of t0, but that is b. So you will have b and you have c. Okay, so that matches. B0 and C0 were the 0th coefficients in the power series expansion, and because these are constant quantities, these are the ones which show up as the 0th coefficients. Okay, so this will be the indicial equation, in other words, the auxiliary equation of the Cauchy-Euler form. If for example M1 if M1 and M2 are two roots, okay. Let's just find the solution for M1. In that case, all you have to do is to put M1 in this equation. Let's just put that. In this case, each AN for M1 will be what? Well, if you look at it, you can put M1 here, so you will have something over there, okay? But here, the summation ranges from 0 to n minus 1. K ranges from 0 to n minus 1. So what is the smallest index of B here? The smallest index is when K reaches the maximum n minus 1. When K reaches n minus 1, you would have B1 here. And similarly C1. That's the smallest index of both B and C. Okay, so all the indices in this sum of B and C are greater than or equal to 1. But the indices more than or equal to 1 are all 0. So these are the coefficients in the power series. And in the power series of B and C, starting from 1 up to infinity, all the coefficients of 0. So if this sum includes coefficients from these two power series such that the smallest index of B and C are 1, then all the indices are 0, because the only indices in this expansion that are non-zero are the 0th indices. Okay, so therefore, it doesn't matter what you put in here, you would always get a 0, because
as k ranges from 0 to n minus 1, all of these indices will be 0. So everything is 0. So the entire lot of all the coefficients of this power series is 0, and so we were finding in 1 for 1, okay, and so all of them are 0. So basically what you have is the trial solution, the solution, homogeneous solution, will be A0 1 with t to the m1. Similarly, if you put in m2, you would have another solution. Let me call that solution 2. Let me call the solution 1. You would have A0 2 t to the m2. And if you remember that these two were actually the homogeneous solutions of, or actually the solutions of this, of the Cauchy-Euler form of differential equation, and a linear combination is just, so the general solution is just a linear combination A01, which is a different coefficient from A02, t to the m1 plus A02 t to the m2. Okay, that's the general solution. So really, the Cauchy-Euler form is a special case of this Frobenius method, where these two b and c, they are constant functions, and the constant functions will have only the zeroth coefficients as whatever the constants are, and the rest of them 0. That's why you get all of the coefficients a_n's as 0, and you're left with only the term that you started with, t to the m1 and t to the m2, and this will be your general solution, which is what we got the last time. Okay, all right. So that really finishes today's lecture. Just a small example of how the Cauchy-Euler example actually fits into this entire scheme of things. We will take up more non-trivial examples and solve problems using the power series solution and the Frobenius method in the next lecture. So, all right, thank you.